Welcome, everybody. In the interest of starting on time, I'll get going. I'm Lynn Harvey, incoming chair of the CSSE. Today we have a series of exciting events. First, you're going to hear some updates from our grand challenges. Jens Oberheide will talk about lower atmosphere weather impacts on the ITM. Titus Yuan on gravity waves in the ITM and cross-scale coupling. And our newest grand challenge, Leslie Lamarck, will be talking about polar cap patches. Then we'll hear an early career highlight by Kamal Kumari. Her topic is sudden stratospheric warmings and geomagnetic activity interactions. We'll hear from Bill Schwartz on the EASY mission. And then we'll hear from the Strategic Planning Committee. You all received a survey last week, and they'll be reporting results of that survey. We'll then go to breakout sessions, have lunch, have more breakout sessions in the early afternoon, and then move on to posters. And around 6, you'll either be helping with poster judging, or you'll be going to the excursion, which is the Iowa Cubs baseball game, or that event may, in fact, get rained out. I'm going to tap into my classical meteorological training and be forecasting the event all day long. If it's a go, we will meet in the Hilton lobby at 6 p.m. If it's not, we'll try to figure out something else to do together. If you're a poster judge, the meeting room where you'll do your deliberations and have lunch and have dinner is the boardroom 2. And if we do end up going to the Cubs game, there are no backpacks or purses unless they're clear. So that's one of the rules. Don't show up with a backpack or you'll be sent away. All right, so I look forward to today and all of the events I just listed, and let's start the agenda.
So welcome everybody. I'm sure you all know me. I'm the outgoing CEDAR Science Steering Committee Chair. So I just wanted to come up and welcome everybody to this meeting. As I think has been said many times, that it's been an enormous amount of work to get us to this meeting, and in particular to get us to the joint CEDAR and GEM meeting. Looking out here, I notice the room is considerably less full than it is when we're all together. We haven't had a CEDAR GEM meeting since 2016, so it's very exciting that everybody's all here. I think Lynn has gone through the events of today, so we don't need to do that. So I really just wanted to come up here and pass on my welcome to everybody to this meeting and my appreciation to everybody who has been able to come here. I know it's been difficult, both in terms of funding and in terms of weather and cancelled flights and what have you, but it's excellent to see everybody here, and it's exciting to see the CEDAR part of this joint meeting kicking off today. So I will hand over to Romina, who will be the chair for this session this morning.
Thank you, Mark and Lynn. Good morning, everyone. So today we have a very packed schedule, so in the interest of time, we just jump in. So as you know, CPAS plays a central and managerial role in the CEDAR workshop, handling all the entire logistic for the meeting planning, scheduling, registration, student support, and many other things that we need for the workshop. This morning, we are super excited to start the session by welcoming remarks from the CPAS Director, Han Muriello.
Good morning, everyone. My name is Hannah Moriello, and I am the UCAR SPS CPAS Director, who has the pleasure of working with NCAR's High Altitude Observatory, HAO, for many years. I'm very happy to welcome all of you to the 2025 Joint CEDAR GEM Workshop. The National Science Foundation CEDAR, or the Coupling Energetics and Dynamics of Atmospheric Regions program, researches to understand the fundamental properties of the space-atmosphere interaction region, identify the interconnected processes that define the local and global behavior, the evolution and influence on the Sun-Earth system, and to explore the predictability. This mission is continuously evolving to anticipate the next generation of scientific breakthroughs and foster cross-disciplinary activities by exploring connections between CEDAR science and other disciplines. GEM is the National Science Foundation's Geospace Environment Modeling Program. This initiative aims to coordinate and focus research on the near-Earth portion of geospace from the lower ionosphere to where the Earth system interacts with the solar wind. The purpose of the GEM program is to support basic research into the dynamical and structural properties of geospace, leading to the construction of a global geospace general circulation GCM model with predictive capability. Yesterday, we are very excited to bring together these two complementary research communities for an inspiring week and discovery, learning, and collaboration. Today, we welcome nearly 400 attendees, including 100 members from our global science community and 100 students, half of which received NSF to support to attend this important meeting. Each of these bright minds is united by a shared mission to deepen our understanding of the complex and dynamic space-atmosphere integration region. Throughout the week, you can look forward to an engaging lineup, hands-on workshops, lightning talks, poster sessions, student-focused activities, and yes, plenty of opportunities for connection and fun. In closing, I would like to take this opportunity to express my sincere gratitude to NSF for their long-standing commitment and support. I also would like to thank the CEDAR and GEM communities for their support. Many thanks to the CEDAR Steering Committee for their unwavering support, as well as Liang Qin from HAO, who is our liaison to the Steering Committee. And last but not least, our own UCAR CPAS event and travel team, Maggie Pear, Jessica Martinez, and Rebecca Cribelli, and also Tracy Baldwin, our CPAS Assistant Director, and they will be here all week. We know many of you have traveled far to be here, and we're truly grateful for your presence. Welcome to Iowa, and welcome to the vibrant, curious, and collaborative spirit of the 2025 CEDAR GEM Workshop. Thank you.
Thank you very much, Han. We really are appreciative of you taking the time to joining us in person today, and many thanks for the whole CPAS for making the CEDAR so smoothly going for us. Next, we are going to hear reports from our Grand Challenge workshops, and for the first one of these series, we have Jens Oberheit to present the first year report on the Grand Challenge on terrestrial weather, on space weather of the ITM.
So good morning, everyone. I'm Jens Oberheider from Clemson University, and I was asked to report on the first year results of this Grand Challenge workshops on behalf of the convening team. So this Grand Challenge workshop is about what's terrestrial weather, and that means the weather of the troposphere and the stratosphere, doing to the IT system. So in a way, the coupling of weather and space weather. And what you see on the screen is, I would, at least in my personal opinion, one of the best illustrations of what we are really after. And from my experience, that's also the kind of graphics that really helps to communicate how this kind of lower upper atmosphere coupling works and why we should actually care about that to a more general audience who's not really expert in our field. So on the left, you see color-coded basically the jet stream in the upper part of the troposphere. In red, very strong wind speeds, 50, 60, 70 meters per second, blowing over the Rocky Mountains, producing a lot of gravity waves. The gravity waves can be tracked in the stratosphere. That's the center panel. These are observations from space, from the Airs spacecraft. So we are looking at 50 kilometers, roughly, gravity wave activity. And then to the right, that's what we are all familiar with, these impressive concentric wave patterns from the GNSS measurements in the ionosphere. And so this event, which was the great North American winter storm, which I'm not going to forget because I was out of power for about a day in South Carolina and it really got cold there. So that really shows that weather events that everyone can relate to, including the general public, really does a lot of stuff in the upper atmosphere and steers up what's going on there. So how do I... Okay, so that means the scientific motivation of this Grand Challenge workshop is all about advancing the understanding of whole atmosphere interconnections between terrestrial and space weather, and what we are trying to do is to do that through combined modeling and observations across different spatial and temporal scales. And the plan for the whole workshop was last year, we talked more about the observational baseline and the state of the models. So we had 16 talks and about 90 or a little bit over 90 people in attendance. So quite a good feedback from the community there. This year we are focusing a little bit more on data model comparisons and also look more closely into the impact of data assimilation. Due to travel restrictions, some of the talks we were hoping to see here could not be presented, but we were still able to put together a very strong program. And so I hope that attendance will be good, despite a Friday afternoon spot that we were assigned to. And so next year, in the final year, we want to finally focus more on the physical mechanism, what's going on. Okay. So I'm not going to read that in detail, but these were some of the data and models we heard about last year from global models, plasma sphere models, whole atmosphere models, down to high resolution gravity wave modeling and all kinds of different data sets there over different scales. And a subset of the workshop results from last year were just accepted as a review article in Surveys in Geophysics, and that should come out within the next few weeks or so. Okay? And finally, that's my last slide. That's a program. So Friday afternoon, so everyone who's still around on Friday afternoon, please consider to attend that. And I think we have a very exciting program that carries all the different aspects of how weather connects to space weather from the different scales, from small scales to large scales. and also talks that address recent progress about high-resolution modeling and also how to extend, for example, the GEOS system up into the thermosphere, so, which I think will be a tremendous tool for the whole atmosphere. Due to the travel restrictions, we will also broadcast this workshop via Zoom, and you can find the Zoom link on the workshop agenda. Okay, thank you.
Thank you very much, Jens. We really appreciate the updates. Next on the agenda, we have Titus Yuan, who's talking about the next Grand Challenge workshop, which will be the second year report on the role of gravity waves in the mesosphere, thermosphere, and ionosphere cross-scale coupling.
Thank you.
Titus, you have 5 minutes.
Okay, yeah. So, let's see. All right. So over the past couple of years, this GC workshop have addressed the significance of a small-scale gravity wave impact in the upper atmosphere, mostly MLT region, and also ionosphere. The recognition is the model, high-resolution local model, and the GCM have advanced greatly to simulate these small-scale gravity wave impact in the MLT and ionosphere, especially for the TEC disturbances observed by the GNSS. So we have also the global scale mechanical model to a high-resolution mechanical model to simulate the gravity wave perturbation in temperature, wind, and density. And seems the simulations are more or less in line with the limited observation that are available. But what we want to address is the need for high quality, large quantity, high resolution gravity wave simulation in the critical region. The critical region we identified is in the mesopause region. It's in this line, if you can see it. Yeah. But currently, these kind of observations are limited mostly locally. But we have traditional observation of gravity waves that use LiDAR imagers, and even put LiDAR and imager on the airplane to flow over hot zones to do these important observations. But we call for global coverage of this small-scale perturbation observation. And last year, we have the first preliminary gravity wave observations from the NASA All mission. As you can see, the small-scale, we can now have a observation of a small-scale wave in the mesopause region globally. There's some presentation about the examples of the preliminary observation. You can see anyway, you can see on the right-hand side, there's small-scale perturbations in large region. And the all also has the first scientific studies using these high-resolution global gravity wave observations, and this is assessed gravity wave variation during the SS event in 2023. Yes. So these are the sort of conclusions that we had last year, and also including the first year. And this year we will have more exciting presentations about new observations, for example, from all, and also the advanced model that can combine the amazing observations currently have with the new physical models. So that's all I have for today. Oh, so we will also have a Zoom session in our workshops this year. Yeah.
All right, thank you very much, Titus. Okay, next we are pleased to have to announce that we have a new Grand Challenge workshop, which is on redefining polar cap patches, and Leslie Marsh is going to introduce that to us.
Hi, good morning, everyone. So this is our new Grand Challenge this year, is on polar cap patches. So the official title of this Grand Challenge is Redefining Polar Cap Patches, Understanding High Latitude Irregularities and Their Implications for the Coupled MIT System. All of us at times prefer to use the simpler phrase, what is a patch? And this is actually, it sounds like it's a simple question, but as we talk about it, it's really not. So the traditional view of what a polar cap patch is the official definition is a plasma density enhancement in the polar cap that is twice the background density. So they're basically these blobs of, blobs of plasma that are kind of independent islands that are basically floating through with the background convection, kind of like you would imagine something floating on a river. Kind of properties that we generally talk about or accept as true. They're large-scale phenomena, so 50 to 500 kilometers-ish. They, as I said, move with the background convection, so you normally have some fairly strong convection in the polar cap, and they're kind of just moving along with it. And then they are traditionally thought to have some, be unstable on the trailing edge due to the gradient drift instability. So there's a kind of the classical thought process is you have this density blob and it ends up with some kind of structuring on the trailing edge moving this way. So that's the classic view of what these things are. So the history of these, they were originally observed in the 60s. There were a bunch of papers in the 80s that really defined what they are, and that's basically the definition I just gave you. And those haven't, and that definition hasn't changed much to today. There was additionally some work in the 90s done with the formation of patches in the day side and the theories of how those were formed, and their peak occurrence. And there has been work done since then, but a lot of it is mostly based on the premise that these are a thing, they exist, and how do they, what kind of structures do we get on them? Do they scintillate? Where do they scintillate? All of those things. So now I'm going to, so patch, double the background density, isolated blob. Now I'm going to go show you a bunch of things that probably could also meet that definition. And this is why this really becomes an interesting topic and something we really feel like we need a grand challenge to reinvestigate and redefine. First is what I just talked about. You have these blobs of plasma. They break off the day side. So this is your day side plasma that's dense and highly ionized. You kind of somehow get these chunks that come off and then go through the top of the polar cap. Next are these so-called hot patches, which the difference between those and the classical patches is that instead of your dense blob being cooler than the surrounding plasma, it's hotter than the surrounding plasma. The general thought is those come from some variety of soft precipitation. Tongue of ionization is very similar to what I just described as a classical patch. But instead of breaking up into segments, it's a continuous kind of stream of ionization. And the trick of this that's really important is we have very sparse measurements at high latitudes. It's very hard to field instruments either in the Arctic or the Antarctic. You don't have a lot of GPS satellites going over. You don't have a lot of satellites, period. So this kind of picture where we have, oh, look, that's lots of holes in your measurement, tends to be on the lower resolution scale. That's pretty typical. And when you have a picture like that, it's pretty hard to tell whether those are actually discrete blobs or a single thread. So there's a kind of back and forth of when you're talking about tongue ionization and we're talking about patches, are you actually talking about two different things, or are you just looking at the same structure through different views? Sun-aligned arcs. So these are auroral structures that go across the polar cap. They're also called theta aurora or polar cap aurora. They typically extend along the sun-Earth line, which sounds kind of like your tongue of ionization or your stream of patches. They also cause density enhancements. Poleward moving auroral forms, PMAF, auroral structures that move into the polar cap. So again, you have these blobs of dense plasma entering the polar cap. This is a somewhat new idea, but traveling ionospheric disturbances. And this is this idea that these are some observations from Shengrong, and sorry, I keep doing the clicker wrong. It's a little hard to see, but basically, if the edge of these bars here are showing what look like very traditional wave-like behavior, like you would see at mid-latitudes, but up above 70 kilometers, or 70 degrees magnetic latitude. Atmospheric gravity waves. So again, something that's very common to see in lower latitudes. We don't talk about it a lot at high latitudes, but why wouldn't they be there? And can we tell the difference between that and these other things? So if you say the definition is just a blob of density that's twice the background, there's a whole bunch of things that could be. So part of this grand challenge is the goal of, well, do we need to refine that definition some? So here are some things that we actually had a workshop last year that came out of this as potential things to look at as to how to start differentiating between some of these phenomena more correctly. Temperature, so is it hot plasma versus cold plasma, which might indicate if it's precipitation driven or kind of solar illumination driven. Is it moving with the background convection, or is it more like a wave-like behavior where you have something propagating on top of velocity, the flow? Polar cap boundaries, that actually matters a lot, because whether something is in a auroral arc or whether something's one of these polar cap phenomena depends on you being able to define what the polar cap actually is, and it moves. So that's a critical factor in a lot of these definitions. And then the final thing that we talked about is, well, maybe none of this matters and we just focus on the impact of patches. So it doesn't matter where it came from, it doesn't matter why it's there. What we really need to be able to say is, if you have a dense enough blob that you're going to cause scintillation or HF refraction or something, we're going to call that a patch, and otherwise, so it's really more of an operational definition than anything else. So just to drive this point home, this is an example I have had some very interesting conversations with my mid-latitude colleagues with, where they look at this figure and they say, you have beautiful TIDs in this figure. And I look at this figure and I say, we have beautiful patches in that figure. And I don't know which one of us is right, and I don't know that there's an easy way to tell just based on this figure and without a better understanding of what the two phenomena are and where they operate and how they differ phenomenologically. So just in general, this is a kind of nice example of some of the things I was talking about earlier, where you have, realizing it's a little hard to see on the screen, but there's, each of these panels is a step through showing two-cell convection. So this is BZ negative, that's the standard convection pattern we see in the polar cap under those conditions. And you have this kind of blob of plasma that somehow looks like it detaches, although in places it is hard to tell if it detaches or if we just have gaps in the data. and then ends up as kind of an independent thing and somehow travels back along the returning convection cells. So this is really what we are focusing on, and trying to understand what these things are in the polar cap. We know there's a lot of stuff that can happen in the polar cap, and really driving into, instead of just saying, oh, it's a blob, it's a patch, end of story, what do we mean by it's a patch? What does that imply about what the structure does? What does that imply about how it interacts with the coupled MIT system? What does that imply about how it will generate small-scale structuring or anything like that? And so that's really the focus of this grand challenge, is to kind of go beyond this idea that there's a patch, we know what this is, and accept that, no, we actually maybe don't know what these are, and we should at least think very carefully about what they are and think about whether there are actually lots of different things and if we should start treating them differently to make our results make more sense. So again, this is kind of, is it a question of semantic? So is it just language, a definition? And I argue that sort of, yes, saying we can define exactly what this is matters, but beyond that, it also matters to say, I just listed like 5 or 6 different phenomena that have different impacts and will be coupled in different ways. So we need to make sure we're not ignoring all those different phenomena in the interest of bundling everything in this bin of, it's a patch, so it's day-side plasma. And I think that's really important to dive into and examine, and because that will really help us better understand the dynamics at high latitude. And then the other thing is that patches have been something that are very commonly discussed. Some of the things that I mentioned about TID behavior in the polar cap and some of the auroral behavior in the polar cap, that's received a lot less attention. And I think we need to look more, focus on, you know, I can't think of a reason why it shouldn't happen, so we need to look at, does it happen, and can we actually tell the difference? So the themes for this grand challenge for the 3 years, the first year we're going to be focusing on data and modeling resources that are available, the patch generation and dynamics from the ionosphere, and the interaction between patches in the broader geospace system. So we're trying to take advantage of the fact that this is a coupled meeting and really bring in some of our GEM colleagues to understand how the interaction, the ionosphere-magnetosphere interaction really helped drive these things. Year 2, we're going to shift more to this patch versus polar TID generation and the dynamics and how this impacts the thermospheric dynamics. And then also small-scale irregularities in plasma instability physics that are associated with patches. And then year 3, looking at space weather impacts of patches. So again, kind of more of the operational impact. Once we understand from the basic science point of view what these things are, is there a operational point of view where we can say, okay, now that we understand the entire zoology of things that actually happen, are there certain categories of things that we need to worry about for space weather, and can we identify those as, you know, a category? And then finally, actually coming up with a recommendation of how to talk about patches, either a better definition than just twice the background, or a better picture of, yes, there are things that are twice the background that do this, this, and this, but there are also these other things. So some of the unique things we're going to try and do as part of this grand challenge, we're actually going to try and hold a virtual meeting in the spring, in addition to the workshop we're having here at CEDAR. And that's just hopefully going to be an opportunity to allow especially more students to come have an opportunity to present their work, present updates to anything that they've started showed this at this meeting, and maybe interact more so there's more constant feedback. We are going to put forward some data sets that have these phenomena in it and things that we think are good to look at these phenomena, again, to really highlight them. So if there's any students or early career people in the audience who, if you're looking for a project or you do things at high latitude and you think this sounds interesting, we really want to help you get started with that. So we're hoping to put some tools together to make it easy for you to kind of join in with us. There's going to be a very strong focus on discussion in the sessions. That's something we did in the session last year that was very successful. We actually are a little bit restrictive in how many talks we have, so we can definitely have some devoted time and generate some good discussion about all these different topics. And again, I really would like anyone who would like to be involved, please do. Students and early career researchers, please be involved. If you don't typically deal with high latitude things, and anything that I just said sounds interesting or sounds relevant to something you know about, we'd love to have you and hear your perspective. We have 2 sessions. One is this afternoon, directly after lunch. Most of our speakers will be in that session. So it's just the general, I think we have, and we're going to end with about half an hour, I think, for discussion afterwards. Half an hour? Maybe less. No, I think it's less than that. And then tomorrow morning, right after the plenary, we have our second session, and that we only have 5 speakers. So that we should have, I think, almost an hour and a half for discussion, which was intentional, because we really want to take what we learned from all of these speakers and bring it together and figure out how we can use that to answer these questions and what new work needs to be done to better answer these questions. So thank you, and please attend our sessions, and I'm happy to answer any questions. I think there's a few extra minutes.
Yes, there are. Thank you very much, Leslie. Thanks, Leslie, for a great introduction. We do have time for a couple of questions, if you have it. Yes.
Can you talk a little bit about the benefits and consequences of having an expansive definition versus a restricted definition?
Okay, so expansive definition means everything's under the one umbrella, and I'd say right now we have something of an expansive definition. The most restrictive thing about it currently is that we do have that twice the background threshold, and that's, what about 1.9? Like, phenomenologically, that's the same, but if you're having hard cutoffs, that's hard. And I'd say one of the challenges with that is, if you have under that definition things that are driven by lower atmospheric waves, things that are driven by precipitation from the magnetosphere, and things that are driven by convection, that's a lot of different things driven by a lot of different activities, and often people try and say, okay, well, I'm going to look at patches and try and compare things about them. And the scintillation properties, for instance, of all those might be very different. So it's hard to do it that way. And then the risk of having a more restrictive definition, I would say you risk ignoring things that are not the exact thing that you're looking for. So one of the things that we hope to come out with this is, if we come up with a more restrictive definition, I think we also want to say, and here are 3 other definitions of things that you also need to care about. You don't get to just ignore it if it doesn't meet our restrictive definition. But yeah, that will be part of the discussion.
Okay. Any other question for Leslie? Yes.
All right. I am old now. I used to be young, but I am old. And we've been studying patches as a community for years and years and years and years. And what is different now? Like, do we have more data? Like, how can we make progress now, more progress now than we made back in, like, when I was a postdoc and studying patches?
So we do have more data at high latitudes than we have previously. Not as much as I'd like, of course, but over the years, we gradually get a little more and a little more. We've had extensive SuperDAR data sets up at high latitudes now. We have riser data sets, which I work with greatly at high latitudes now. And I think slowly more GNSS receivers. So I think there is more data than there used to be. But the kind of the point of this also is re-examining how we think of these structures. So it's almost, I think this would have value even if we were only looking at the old data too, where if we say, okay, well, we've had this picture, we've all had it in the community of our mind as this is what this phenomena is, and we have all this evidence, and if you look at papers, you have things that say, oh, there's like the scintillation only on the trailing edge. Oh, there's scintillation only on the leading edge. Oh, there's scintillation in the middle. That doesn't fit in this paradigm. There's all kinds of observations that have been published that I'm sure you've contributed to that don't fit in this paradigm of what kind of a patch is. So we're trying to say, okay, let's take this opportunity to re-examine that paradigm with all the research that's been done and with the research that's currently being done, and can we better understand it as a community and how come up with either both some language to talk about it better and just an understanding as a community better than kind of a overly simplistic view.
All right, great. Thank you very much, Leslie. Let's thank Leslie one more time. We'll look forward to the impacts from this grand challenge in future. Okay, so next we move on to our early career science highlight, and please join me welcoming Komal Kumari, talking about the interactions between geomagnetic activity and sudden stratospheric warming.
Okay, so good morning, everyone. This is Komal Kumari, and I'll be, first of all, thank you for the invitation to present this work. I don't know how that happened. Okay, so I'll be talking about interactions between geomagnetic activity and sudden stratospheric warming. So first of all, I want to thank my mentor, Dr. Nick Patella at NSF NCAR HAO. And I also want to thank ASP postdoctoral fellowship opportunity to support this work. And I also want to sincerely appreciate insightful contribution from my colleague, Dr. Kwon Gan and Dr. Chi-Ting Soo. So in terms of geomagnetic activity, I'll be mainly talking about geomagnetic storm event. Both storm as well as sudden stratospheric warming, which I will say SSW hereafter. So both storm and SSW event represent extreme space weather event that we study in our community. So while storm is typically triggered from the sun, so CMEs, and then they interact with Earth's magnetosphere and then impact ionosphere-thermosphere region. So we know storm as a forcing from above phenomena. And SSW is triggered in the lower atmosphere. So it's generally associated with a rapid warming of the polar stratosphere region and the reversal of the zonal wind from eastward to westward direction. And it generally happens from over Arctic from December to February months, so during northern winter months. And it's also associated with enhanced global scale wave driving, so propagating from lower atmosphere and above, and then subsequently it impacts ionosphere-thermosphere region. So some of the key effects of storm as well as SSW that we already know in our community. So storm can impact thermospheric O2N2. So thermospheric O2N2 can decrease over mid to high latitude and decrease at mid to high latitude and increase at low latitude. And while sudden stratospheric warming event has opposite effect over low latitude, so it can decrease the thermospheric O2N2 over low latitude, and that mainly has to do with enhanced global scale wave driving impact on residual mean circulation. And in terms of ionospheric electron density or total electron content TEC. So TEC can have both positive and negative effect during storm as well as SSW, and that depends on what longitude we are looking at, and in SSW case, what local time we are looking at. So that's just overview of how a storm and SSW individually impacts ionosphere and thermosphere region. Here I'm going to show a case study of 27th February 2023 storm. And during the storm, as you can see, the KP was equals to 6, so storm time condition. And I'm also showing the F10.7 index here in the top plot. In the bottom plot, I'm showing the stratospheric polar zonal wind. So you can see that the zonal wind had reversed from eastward to westward direction exactly when the storm had occurred. So and I'm not showing the temperature plot here, but the temperature had also increased. So it's a perfect indicator of SSW event occurrence. So this is a perfect opportunity to study how strong forcing from both above as well as below, how they both together impact the ionosphere and thermosphere region. And also it's an opportunity to highlight how the SSW preconditions the atmosphere due to lower atmosphere forcing to study for storm impact on the ionosphere-thermosphere region. All right. So for the analysis, I'm using SD-WACOM-X model runs. So SD-WACOM-X is a whole atmosphere model. Basically, it can simulate the atmospheric variability from troposphere, stratosphere up to ionosphere-thermosphere region. And at the lower boundary of SD-WACOM-X model, we use META-2 to nudge the lower boundary condition up to stratospheric altitude. And that allows us to nudge the realistic day-to-day variability coming from lower atmosphere in the model. So, and that's because META-2 is a reanalysis data set based on assimilated meteorological observation. So here I'm showing a SD-WACOM-X a plot of 2009 SSW event from Paetala et al. 2014 paper. So you can see how the SD-WACOM-X can simulate SSW event from surface up to 500 kilometers using the META-2 at the lower boundary. So you can see the wind has reversed in the lower altitude from eastward to westward direction, so from red to blue color, and then further the effect is propagated upwards in the model. So for the analysis, I'm actually using I'm conducting two model runs here. So in the first run, I use hourly META-2 data at the lower boundary, so I have realistic day-to-day variability coming from lower atmosphere. And I also have realistic KP and F10.7 condition included in the model, so it can be used to study for storm response. And for the second model run, I am keeping the storm, but removing the SSW effect at lower boundary, and for that, I am using the 40 years of META-2 data, and I'm just taking the 40-year mean, so daily mean, so that is basically the climatology. And this taking the 40-year mean allows me to remove day-to-day variability coming from lower atmosphere, as well as the SSW-induced variability at the lower boundary. So in the rightmost plot, you can see how the climatological zonal wind in the stratosphere region looks much smoother than the condition that is included in the first run. So for the analysis here, I'm calculating the storm response in both runs, and then that's what I want to compare to really understand how the SSW is playing role here in terms of storm impact on the ionosphere-thermosphere region. So basically, the typical method of calculating the storm response is subtracting by a quiet day just before the storm. So I'm using 24th and 25th February when KP was less than 3, so non-storm condition, and that's what I'm subtracting. So all right, so here I'm showing you the storm response in thermospheric O2N2 and ionospheric TEC in both runs. So first column, you see that is from first run where SSW is included at the lower boundary, and in the second run, the second column where the SSW is excluded. And on the y-axis, you have latitude, and on the x-axis, you have hourly data from 26th February up to 1st March. So, and another thing I want to point out that I have overlaid a red line over the contour plots. That is basically the KP index, so that is telling you when exactly the storm occurred. So maybe visibly you can see there are some differences between these two run results. So mainly one thing I want to point out that after the storm is already done during the storm recovery period, which is on 28th February, you can probably see the most difference at the low latitude. So what is happening that when the SSW is included at the lower boundary, the storm recovery is happening much faster. And in terms of quantitative comparison, I have also included the line plots in the third column where that's a low latitude average of the storm response from those contour plots. And what we understand from the comparison of these two line plots that it's about 20 to 50% changes that is happening due to SSW. So from the next slide, I will just show the difference of these two plots, these two run. And that is what I want to understand to highlight the lower atmosphere preconditioning effect due to SSW. So here I'm showing the difference of those two runs. So this is thermosphere O2N2 and TEC, and I'm showing you the 24-hour mean, so mean state changes, and during storm recovery, so on 28 February, because that's where we see the most difference between these two runs. So, okay, so maybe one thing is easily, you can point out that the thermospheric O2N2 changes are mostly over 50 knots over mid-latitude, and the TEC changes we see mostly at the low latitude from plus minus 30 degree latitude. So, it's interesting because we know that the thermospheric O2N2 has directly impacts the production and loss of O+ ion in F region, and that would also affect electron density in the ionosphere region. So, so why don't the O2N2 changes appear to correlate with the TEC variations? So the answer is that I need to look into the NMF2, which is peak electron density at 250 kilometer in the F region, and TEC is more like height integrated electron density, so it was not, it didn't appear there. But in the peak electron density, I'm able to see that the thermospheric O2N2 changes directly correlates with the peak electron density changes over mid-latitude. Over low latitude, you can see that that something else is going on than the thermospheric composition. So it's not driven by thermospheric composition changes, and that is over low latitude. It's basically due to the plasma transport mechanism, so through E cross B drift and the field aligned drift, and that is what playing the role. So these are my quick conclusions. In the interest of time, I didn't show more results. But these are the main takeaway points, that the SSW preconditioning leads to 20 to 50 variations in storm time electron density and thermospheric O2N2 changes, and it can accelerate the post-storm recovery. And thermospheric O2N2 changes we saw prominent at mid-latitude, and electron density changes at both mid and low latitude. At mid-latitude is mainly correlated from the thermospheric composition, and which is changing electron density through ion neutral chemistry. And at low latitude, dynamic transport mechanisms are playing the bigger role. So I didn't show more plots here, but we also did further study like how exactly the dynamic terms are changing the electron density, and we found that that's through terdiurnal and semi-diurnal effect due to SSW preconditioning at lower boundary. And we also investigated why do we see the thermospheric O2N2 changes only over mid-latitude, and that we understood that it's mainly due to how the storm is reacting to different background introduced by SSW in the first run versus the second run. So that's my conclusion, and you can look for our upcoming, we will submit the paper soon, so yeah. So thank you.
Thank you very much. We don't have time for questions, so please, if you have any question, catch Kamal later offline, and she'll be happy to answer that. Thank you very much, Kamal. All right, so next, let us move on to the science highlight of the session, which is about EASY mission, with the primary goal of mapping auroral electrojets. As you know, EASY was launched in March of this year, and we are excited to have Bill Schwartz and Rafael Mesquita to present the first results from the mission.
Great, thank you very much, Romina. Yeah, very pleased to present some of the first results from the EASY mission, which is a mission that rarely lives up to its name, but we love it. I'd like to acknowledge some of my co-authors. So Rafael Mesquita, who's our deputy project scientist, now in Phase E, is going to present the latter portion of this talk. And all of us who are that are in photographs here are actually at this conference. So if you have any questions, seek us out, and one of us must be able to answer your questions. I'd also like to acknowledge our partners at JPL, who provided the instrument hardware, and Blue Canyon Technologies, who built the commercial CubeSat buses for us. So the E in EASY is electrojet. So our science questions deal with the spatial and temporal morphology of the electrojets. I don't have time to go into those science questions themselves, but our primary focus is the auroral electrojet, and if things go well, we have augmentation science for the equatorial electrojets. So the Z in EASY is Zeeman. So we infer the electrojet currents based on their perturbations of the geomagnetic field, and we can remotely sense the geomagnetic field close to the electrojets using the Zeeman effect. So there are certain spectral lines in the atmosphere that are split in the presence of a magnetic field, and that split is proportional to the total magnetic field. There are also some other beneficial magneto-optic effects that mean that the relative orientations of the look vector and the magnetic field vector is actually captured in the polarization state of the radiance that we measure. So we can infer and retrieve what the vector magnetic field is. So the I in EASY is imaging, and EASY is a 3 CubeSat constellation, if you want to use the constellation term generously. There are 3 CubeSats in a pearls on a string orbit configuration. Each is carrying a microwave instrument that has 4 independent antennas and receivers measuring thermal emissions from the O2 118 gigahertz thermal emission. And so we essentially have 12 radiometer, largely independent radiometer instrument in our fleet here, and they can resolve spatial information of the electrojets. You can see how they're spaced there, so we can resolve scales between 150 and 750 kilometers on the ground. And we also have temporal information. So the signal that we're measuring is originating between roughly 60 and 100 kilometers altitude. It peaks at about 80 kilometers. And from these measurements, we can derive 2-dimensional equivalent current maps. And as I mentioned, pearl on a string configuration, each spacecraft is about 2 to 10 minutes behind the one before or behind. We can actually control that spacing using differential drag. So we don't have any propulsion on these CubeSats, but by orienting the spacecraft, we can control that separation and control that temporal sampling as well. So we were deployed from a SpaceX rideshare back on the Ides of March. We were 3 of 74 small payloads that were deployed. We are, and there goes the second one of our 3. We are in a almost 600 kilometer sun-synchronous orbit. Very circular, very good. I'm not gonna wait on EZC, but trust me that it's up there, and I'm happy to report that mothers and children are all doing well, even to this day. So currently we are so we just finished our commissioning about 5 weeks ago. So we're in our first northern AEJ season. And so we have a daytime ascending node, and what we observe the electrojet region, auroral electrojet region, every orbit, so about 15 or 16 times a day. We start our observation on the day side and end when we cross 55 north magnetic latitude on the night side. So we have a 9-minute observation. We have about 90 seconds of dark sky observations before and after for calibration. And our separation right now between the spacecraft is about 3 minutes. And you can see in the bottom there how during our auroral and equatorial electrojet seasons, we plan to vary the separation so we can get that different temporal sensing. So we'll vary between 2 and 10 minutes. So putting the cart before the horse a little bit, the data are not available yet to the public. We will release them in mid-November after 6 months of nominal operations, but we will be releasing the level 1 geolocated calibrated brightness temperatures from the MEM radiometers, level 2 vector magnetic field retrievals at 80 kilometers, and level 3 two-dimensional auroral electrojet currents. And we have an easy gateway that the QR code points to. It has everything but the data themselves, but a lot of other information about the mission. So this is our first light, and maybe Raphael can start making his way up here. He'll talk a little bit more about the data. He did this, actually, I don't have it running. This is why our presentation is so large. But yeah, you can see the 4 different polarizations, vertical and horizontal, linearly polarized signal, as well as the second and third Stokes parameters. So, Raphael.
Thanks, Bill. All right, thanks, folks, for letting us talk. Yes, so continue on what Bill said. So there's a lot of information here. So for starters, you see that the data matches pretty well the theoretical basis for it. This is literally hacked together like overnight when we're actually looking at the data as it was downlinked. It was really exciting time. Here at the you can see the separation between the peaks there. The separation is pretty small because we're crossing the equator where the magnetic field is weaker. And one of the interesting things here, let me see if I can actually make that happen again. Yes. You can see that as we cross the magnetic field, the magnetic equator, the S4 component basically switches from being antisymmetric one way to the other. So what does that mean? That means that we can actually get the directions of the magnetic field as well. In spite of us actually not having many different directions of measurement. So coming from there, so a little bit of an explanation here about what we use to actually do the retrievals. So there's this paper from Richard Larson at 2014, so it explains everything there. Sorry, there's a lot of information here, and I try to pack as much information as possible because I know this is going to be available for folks. But please come talk to me and Sam, and we can talk to you guys more about it. But the important thing here is that there's a lot of let me see if this works. Yes, there's a lot of things that affect our spectra, and one of the things that we want to be mindful of is that, one, the magnetic field strength and the direction is going to affect the spectra. You can see that those angles, theta and eta in the image on the right, those are very important to determine what the direction of the magnetic field is. And you can also see here, there's some minor explanation about, what if the direction between the magnetic field and the line of sight is parallel or perpendicular? How does the spectral behave? Anyway, so here's the most recent calibrated data. So this data is corresponding to one of the substorms that we've been looking at. I know it's really not easy to actually look at it and see hey, there's a substorm here, but trust me, there is. So what we measure is a vertical linear, horizontal linear S3 and S4 in the modified Stokes. The vertical, horizontal, and the S3 polarizations are symmetric. I ask you to ignore for now the S3 because we're still making a lot of progress in calibrating that. And S4 is anti-symmetric, as you can see. So each of these 9 minutes, 15 passes a day that Bill talked about, we have a spectra every 2 seconds. We have 1024 channels. We have 4 look directions and 3 spacecraft. And I'll tell you, it's a lot of data. All right, so this is what all four look angles that we have look like. So if you look at the thing that I want you guys to note is that, like, you can see that although they look a lot alike, but there's just very different, the spectra in the nitty-gritty of it, they're very different. So meaning you're measuring 4 different atmospheres, 4 different magnetic fields, and there's a lot of information here. All right. So for the L2, the provisional L2, the ones that I'm going to share with you guys, we're basically doing like the quickest, most simple retrieval, which is the total B. So we can infer the total B by like measuring the distance between those 2 peaks. While we fix some calibration, improve the calibration, we're going to be using this to actually do our assessment. So if you actually just measure the distance, the separation between those 2 peaks, you can actually get like a retrieval that looks like the stuff that are on the bottom here. I know it's kind of hard to look at and kind of hard to see, but there's our GRF and also the measurements from EASY. And at the top right there, you have IGRF and EASY. So it's that's happening right at the recovery of that little magnetic substorm there. All right, so when we put that through our L3 algorithm is such that we can actually retrieve the currents, the horizontal currents from just the total B. That's what you get. And you can see that there's like, it's very easily to see that there's something going on there. All right, so one of the things that we've done is like, how does that compare to, our current method, which would be SuperMag. So there's only, I think, 9 magnetometers on the right. And you can see that, like, in general, the currents behave in a very similar manner. This is SuperMag going through the same retrieval as EASY does. Now, if I project the EASY onto the ground, EASY measurements onto the ground, this is kind of what it looks like. All right, so there are a bunch of caveats here. I'm not going to get too much into it, but please just come and talk to me and Sam, and we'll, discuss everything. So yes, the top right there. So what I really wanted to drive home here is the interest in the CEDAR community, like what's in it for all of us, right? So basically, we will be able to, at some point, retrieve the neutral winds. That is something that's very simply done. Quick and dirty, I've already done something like, looks like that it could work. So basically, you find the center of the spectra. By the physics of it is just that the spectra is symmetric, and you can use that to your favor. So when you find that, the center of the spectra, and you know very well what the line of sight, what the spacecraft velocity is along the line of sight, you can actually get the line of sight velocity residuals, which in theory are related to the neutral winds. And we can also get a lot of information about the temperature, and the more important part is that we get a temperature profile. Well, how do we do that? So there's a way to actually translate a frequency domain into altitude pressure domain. What you look at here in the bottom right is the actual contribution functions for easy in terms of temperature. So the way to look at that is that anytime that the red point, the red part of the spectra on the Jacobians on the bottom right is 1, you have like an increase of 1 in the spectra at that frequency range. So it's really like an intricate retrieval and still needs a lot of work, but you can already see here, for example, you have the measurements there in red at the top right, and then you have a certain you have a certain blue, what we call the L0B, which is basically like the theoretical approach to it using just EMSIS. And then I impose a certain modification to the EMSIS profile, and the measurements, we approach the measurements a little better. All right, yes, so this is our sensitivity. So, I mean, I know this is a lot, and there's a lot to actually ingest from this, but I'm leaving here, guys, with some reading materials, our emails, and please come talk to us. We are excited. We have a lot of good stuff to share, and we're looking forward to talking to you guys. So if you guys have any questions, thank you.
Thank you very much, Bill and Rafael. We have time for a couple of quick questions. Yes, Tomoko.
Congratulations, very exciting.
Thank you.
So I have a question about effect of lithospheric field.
Mm-hmm.
You sensing currents flowing very low, and then do you guys are thinking about how to incorporate effect of lithospheric field getting into the data sets to determine a perturbation B to detect
Right.
the currents? So
Right,
it's,
yes.
I think basically background removal effect of lithospheric field.
By mesospheric field, do you mean?
Lithosphere surface
Oh,
field.
no, yes, thank you. So this is kind of an interesting topic, but through the radiative transfer, we see that the stuff that actually comes from the surface do not reach the spacecraft. So basically, what we do is we just imagine a layer between 0 and 1 kilometer. We have to calculate the production in that layer and then propagate upwards, right, towards the spacecraft. So when you get to the kilometer above, you actually have to calculate the production and the absorption there. So we see that everything from the ground up to about 30 kilometers or so gets absorbed out locally. So as you move higher up, you start seeing the actual all right, some of that radiation made it into the spacecraft, maybe 35 kilometers and above that. So that's where we see that here in our contribution function, basically. You see that below, what's that, 35 kilometers, you basically have almost no contribution at all.
Okay. Thank you, Rafael. Any other question? Yes.
Yeah, I have a quick question. But firstly, congratulations. This is really nice-looking stuff. And it's not often that you get a fundamentally new way of doing business coming online, and that's what this is. It's just something we haven't seen before. So congratulations for that. But being a neutral winds guy, my antennae tuned in onto your comment about neutral winds. Could you say something about the altitude range that you would be sampling with that technique?
Yes, so it's a little tough. So basically, you have the same idea. The contribution function is there, and the signal is coming from different altitudes, right? So if you think about it from the standpoint of all right, everything is being producing radiation here at lower altitude, and you look at the mesosphere more or less as a filter. So you have those absorption lines. It's hard to really pin down, but with the contribution function, we can actually infer it to be about 80 kilometers, plus or minus 5 kilometers or so. That's something that, like, before we actually, like, hey, CEDAR community, here's the neutral wind, we actually have, like, a lot of work to do.
All right. Well, let's thank Bill and Rafael one more time and the whole EASY team. And we look forward to exciting results coming from the mission in future. All right, so we now turn our attention to the final item in the agenda, which is on the CEDAR strategic planning. In order to guide the strategic planning, we wanted to understand the value of CEDAR to you. So recently we sent out a survey and queried the community on the value of the CEDAR program and its science. So now Lynn and Caitlin are going to present the result of this survey.
Thank you, Romina. Yes, this is a brief talk on sort of the activities that the subcommittee on the strategic planning has been undertaking for the last few weeks and months. A year ago, the strategic planning subcommittee was thinking about how we wanted to move forward with tweaking or updating the CEDAR New Dimensions document. But as the conversation has changed, we are now focused on soliciting feedback from the community on the value of CEDAR science and resource allocation. Do you want to change the? Oh. So, as I said, motivated by the situations that we're living in with budgets and NSF, we sent out a survey a couple weeks ago to solicit input from the community on the value of CEDAR science, as well as what you value the CEDAR program spending its money on. We asked for your thoughts and questions to help with strategic planning process.
So as you can tell, Lynn and I are going to switch back and forth on this presentation, but I just want to refresh your memory on what CEDAR supports. One of the things you're most familiar with probably is the annual meeting. And then that also includes the student-centered workshop and student support. But for those of you who are only NASA funded, NSF also provides small group 3-year research awards, which are very important to a number of the people in the community. And then also they provide, the program supports facilities for CEDAR-related observations. This can be everything from ISR to LIDAR to, I think, even rocket campaigns. So CEDAR program does a lot of different things, and they touch all of us in different ways.
So we sent out a survey, and we included just 4 questions to keep it focused. 2 of them were focused on the value of science, and 2 were focused on resources. So we asked what makes the CEDAR program in general valuable to you. We asked which specific CEDAR resources have you found particularly useful for your work and for your students, staff, and group. We asked, what do you think is the primary scientific goal toward which CEDAR resources should be put? And 4th, what is your view of CEDAR's strongest science contribution to the scientific endeavor as a whole? So we asked 2 kind of science-related questions on the value of science and the directions that we're going, and your input on that, and 2 questions on resource allocation, what you found valuable in your career and as your group, on how the money in the CEDAR program has been spent.
Okay, on to the results. So thus far, we've heard from 24 of you. So those people, thank you for taking the time to respond to this survey. But we'd really love to hear from more of you. So we're going to resend the survey, so be looking for that link today. I will try and get that out today. And of the people who responded, we wanted to keep track of the career status of those people, just so we can understand what's valuable to who. So we have, most of the people were senior scientists. We have approximately a quarter that were early to mid-career scientists, and then a handful of student scientists.
So students, please fill out the survey when you get the announcement.
All right, so one of the things about this survey is we wanted to leave it very open-ended. We wanted to hear what you thought without constraining you to canned responses. So that means that we got a lot of different responses. Some were only a couple words long, and some of them were paragraphs long. And from that, I just want to share some of the words that were often repeated. Obviously CEDAR, but a lot of people mentioned the community, the workshop, researching, scientists, student, and then also resources like Madrigal. And these all came up multiple times.
So question number one, what makes CEDAR valuable to you as a scientist? Here are the results that actually really surprised me. I thought, as a soft money scientist, that the people would value the grants, which is the red piece of pie. But the people who filled out the survey really value the community and the annual meeting, the yellow and blue pieces of the pie. So this gives us really good information to work with the CSSC, the GEM community, NSF, and communicate your wishes that you really value this workshop. Moving forward, you want resources to be put toward maintaining this annual workshop.
And by the way, if you disagree with this result, fill out the survey and we'll update it. All right, so the next one is, what specific CEDAR researches have you found particularly useful for your own work and your student staffer group? So the annual meeting actually came up in this response. And the way I classified this is if you're talking about networking and collaboration, that kind of thing, I put it in there. Again, we saw, let's see here. Sorry, the screen is very small over here. Madrigal database came up. A lot of you use the Madrigal database. But there were also, the research grants came up again. But again, I'm a little surprised how few people mentioned the research grants. And one of the reasons that may be is that maybe there aren't enough research grants and not very many of you guys have them. Okay. All right, so this was kind of a challenging question to answer, but this is, what is CEDAR's strongest science contributions to scientific endeavor as a whole? And so the first one was, a lot of people, again, mentioned the annual meeting and collaboration of scientists and networking, and also the development of students, the next generation of scientists. And then B was integration of multidisciplinary observations and modeling. So this is everything from coupling studies of different atmospheric regions, so mesosphere to maybe thermosphere, and then how do models and data and observations interact. And what's interesting to me about the responses is that they were a little generalized in that they followed maybe a system of systems science perspective. And so nobody really came up and said, the most important contribution to CEDAR science is this specific phenomena, say sun stratospheric warmings or something like that. That wasn't really a response. And then lastly, the continuation of research maintenance and coordination of research infrastructure. So that's, again, your ISRs and those kind of things was very important to the community.
But again, we've just scratched the surface. We've surveyed like these 6 tables. So we need for all of you to fill out this survey so that we have the best statistics possible. When we ask this question, what do you think is the primary scientific goal toward which CEDAR resources should be put? Again, half of the respondents mentioned something science-related, but the other half mentioned community, strategic planning, outreach, and training. So it was divided. I was really surprised. I thought 80% would say the research grants, but again, this community and collaborating, the workshops, planning, prioritization, and outreach and training is just as important as the science. Okay, so preview of coming attractions. We'll send out this survey. We really need to sample your opinions. We need to get your feedback. We need to communicate your feedback both to the CSSC, the GEM communities, and NSF. It's critically important that we have this information so that we can be helpful and guide NSF if they choose to take our values and opinions into account in their planning. And please expect yet another survey to follow on where we will ask even more pointed and perhaps difficult questions about the in-person meeting next year. We are dedicated to holding an in-person meeting next year. I'm working with both Mark and the GEM leadership, and we know, and it's been confirmed through these limited survey results, how valuable the in-person meeting is to you. We're committed to doing that, no matter what NSF levels of support are. And in order to do that, we need to be flexible and adaptable and perhaps change our way of doing things. We'll ask questions on what potentially could be reduced, different times of year, different number of people, the specifics of how do you pull off a meeting that's maybe a skinny meeting, right? So please, when you get these surveys, fill them out and make your voice heard. This is the time to share your opinion and get that voice funneled up to NSF so that we can all work together to maintain the CEDAR science community. That's all we have.
Okay, great. Thank you very much. We are coming to the end of the session, but I wanted to see if there are anyone urging to say, to make any comments about all this. It's the time now to do it.
Hi, Romina. This is Shikha here. Can you hear me?
Yes, we can.
Okay, so thanks for putting this survey together. I would like to mention one thing that in one of your slides, you said that CEDAR basically is, CEDAR workshop is funded through CEDAR program. Tomorrow I'm going to, when I do the NSF update, I will be showing that aeronomy is the core program, which is now part of Geospace cluster. And Anna Johansson, who is our DD, she showed in her presentation yesterday that aeronomy core program and all CEDAR program lies within aeronomy. So there are no separate pot of funds.
Okay, thank you, Shikha.
And other thing is that I would also be interested in knowing that how our science impacts the society. So are there any efforts? It would be good that people think of, like yesterday when there was a talk about outreach by Alison James, and I really liked it because she said very clearly and communicated very effectively that how we need to improve our strategies in reaching out to public who are not familiar with scientific topics. And I know there are several people who are doing excellent citizen science work, which includes HAMSCI community. So I would urge and request that there should be coordinated efforts and people should think clearly and what are the effective strategies that we can communicate to outside community, that how our research is important to them.
Yeah, that's a great point. Thank you, Shikha. All right, well, thank you very much, Lynn and Kathleen. So this brings us to the end of the session. Many thanks to our speakers, to all of you for participating this morning. Now enjoy the coffee break and see you in the outbreak sessions later. Thank you.